Imagine an aircraft that can fly from one side of the world to the other for almost 19 hours without stopping. A plane made from millions of parts brought in from across Europe, created to be lighter, burn less fuel, and make long flights feel more comfortable than ever before. That aircraft is the Airbus A350, one of the most advanced passenger jets ever built, designed to compete with the best airplanes on the planet. But have you ever wondered how a machine like this is actually made? To find out, we have to travel to France, to the heart of Airbus, and follow the process step by step as one of the great giants of the sky comes to life. The Airbus A350 was born from a need. Airlines wanted a new long-haul aircraft that could compete in a market dominated by planes like the Boeing 787 and the 777. When Airbus announced the project in 2006, the idea seemed ambitious, but it was not perfect at first. Airlines wanted more efficiency, more flexibility, and a design that could handle the future of international travel. So Airbus went back and redesigned the original concept. The result was a wider aircraft, built with an extensive use of composite materials, lighter than traditional aluminum planes, and more efficient on some of the longest routes in the world. The A350 made its first flight in June of 2013, and in January of 2015, it officially entered service with Qatar Airways. By April of 2026, the A350 had accumulated more than 5,300 orders, with two main versions leading the program: the A350-900, ideal for routes of up to around 8,000 miles, and the larger A350-1000, capable of carrying more passengers and cargo over distances of up to 9,000 miles. One of the secrets behind the aircraft is its structure. Around 53% of the A350 is made from carbon fiber and other composite materials. That makes it about 20% lighter than previous aluminum aircraft, reducing fuel consumption by about 25% and cutting CO2 emissions by a similar amount. And for passengers, the difference is not only in the numbers. The cabin is pressurized to feel closer to a lower altitude, and its advanced air filtration system helps improve comfort during long flights. That makes it especially valuable on ultra-long-haul routes, like Singapore to New York, the longest commercial flight in the world, lasting almost 19 hours. But how is this masterpiece of human engineering actually built? The production of the A350 is a massive international effort. It begins across several countries and ends on the final assembly line in Toulouse, France. Key components arrive from different parts of Europe. The vertical stabilizer comes from Getafe, Spain. The wings come from Broughton, in the United Kingdom. Sections of the fuselage come from Hamburg, Germany, and Saint-Nazaire, France. These enormous pieces are transported by the Airbus Beluga, a giant cargo aircraft designed specifically to carry oversized aircraft parts. A single fuselage section can measure around 20 meters long and weigh several tons, which means every movement requires perfect logistics. Once the parts arrive in Toulouse, the real assembly process begins with extremely detailed inspections. Technicians use high-frequency ultrasonic scanners to detect tiny imperfections inside the composite materials. Quality inspectors examine every detail, from structural bulkheads to pre-installed electrical systems. A single A350 contains more than 60 kilometers of wiring, about 30% more than previous commercial aircraft. Because of its advanced electronic systems, these include fly-by-wire flight controls, modern cockpit screens, and digital systems that constantly monitor the aircraft. The fuselage, with a diameter of almost 6 meters, allows airlines to choose many different layouts. It can carry around 366 passengers in a standard configuration, up to 440 passengers in a high-density layout, or be transformed into a luxury cabin with private suites. At this stage, workers begin installing important interior elements, including the lavatory floors. These are sealed with a moisture-resistant polymer layer to protect the aircraft over its long service life, which can last more than 20 years. Every step reflects the strict standards of Airbus. One mistake, even a small one, could delay production or compromise safety. And in Toulouse, Airbus is more than just a company. It is part of the region's economy. The company directly employs more than 10,000 people there and supports tens of thousands of indirect jobs. But one of the most important parts of the A350 is not the fuselage or even the wings, it is the engines. The A350 is powered by Rolls-Royce engines designed specifically for this aircraft, considered among the most advanced engines in the world. Each engine can produce up to 374 kilonewtons of thrust, enough to accelerate an aircraft weighing around 280 tons to nearly 900 kilometers per hour. At the front of the engine is an enormous fan, about 3 meters in diameter, made up of 22 titanium blades. During takeoff, these blades spin at thousands of revolutions per minute, pulling in more than 1 ton of air every second. The creation of these engines begins digitally. Engineers use advanced design software to optimize every component, improving efficiency while reducing weight. Inside the engine, compressor blades made from nickel and titanium superalloys are designed to withstand extreme forces and temperatures. Some components use single crystal structures, which reduce weak points and allow them to survive the intense heat of the combustion chamber. The temperatures inside can reach levels far beyond what ordinary metals could survive, so the parts are protected with special ceramic composite coatings. These coatings protect the engine without adding unnecessary weight. Modern manufacturing has also changed the way these engines are made. At Rolls-Royce facilities in Derby, in the United Kingdom, high-powered lasers melt titanium and nickel powder layer by layer, creating parts such as fuel nozzles and turbine supports through 3D printing. These fuel nozzles can be lighter, more efficient, and stronger than parts made with traditional methods. A single engine contains more than 30,000 components, from microscopic screws to turbine discs around 1 meter wide, and all of them must be assembled with tolerances measured in microns. Engine assembly takes place in climate-controlled hangars to prevent thermal distortion. The casing, made from titanium alloys, acts like the skeleton of the engine, supporting extreme forces during flight. Technicians install the high-pressure compressor, combustion chamber, and low-pressure turbine, using laser alignment systems and robots to guarantee absolute precision. And before any engine is allowed to fly, it goes through intense testing. Engineers simulate takeoffs, expose the engine to temperatures from extreme cold to extreme heat, and even perform bird ingestion tests to recreate dangerous real-world scenarios. The result is an engine that consumes less fuel than its predecessor and emits fewer nitrogen oxides, helping it meet strict international aviation regulations. One engine can operate for more than 20,000 hours before needing major maintenance, the equivalent of thousands of transatlantic flight cycles. But now, let's return to the aircraft assembly line. The A350 moves through a series of specialized stations, each one with a specific purpose. At Station 50, technicians install the main landing gear, manufactured by Safran Landing Systems. Each unit includes 6 wheels per bogie and is designed to support enormous forces during landing. When an aircraft weighing hundreds of tons touches down at around 260 kilometers per hour, the landing gear has to absorb the impact with incredible precision. Hydraulic actuators connected to high-pressure lines allow the system to deploy smoothly, even in difficult crosswind conditions. Technicians test the system remotely to make sure it performs exactly as it would during a real landing. But the landing gear is not just a mechanical structure, it is an intelligent system. Built-in sensors monitor tire pressure and brake temperature, sending real-time data to the cockpit. This helps reduce wear and improve safety, allowing the A350 to operate on demanding runways, even at high-altitude airports like Bogota. At Station 40, the wings are joined to the fuselage. This is one of the most delicate moments in the entire process. More than 10,000 high-strength titanium fasteners must be aligned with extreme accuracy. Each wing is about 32 meters long and made mostly from carbon fiber. Despite weighing only around 6.5 tons, each wing can withstand loads of up to 400 tons during extreme maneuvers. The wing design is highly aerodynamic, with curved winglets inspired by birds of prey. These winglets reduce drag and improve fuel efficiency. The wings also hold massive fuel tanks with a capacity of around 141,000 litres, enough for routes like London to Perth without stopping. The assembly of the fuselage is another major milestone. Each section can weigh up to 32 tons and is moved between hangars on mobile platforms. It may look simple, but it requires a carefully controlled choreography to avoid vibration, damage, or misalignment. Before the aircraft moves outside, technicians cover every opening, from pitot sensors to windows, with waterproof protectors. This keeps rain, dust, and insects away from the aircraft during the process. Behind all of this is an enormous logistics system. Airbus logistics centers cover around 84,000 square meters, the equivalent of about 12 football fields. These centers are the brain of the operation. An artificial intelligence-based management system tracks each of the A350's 2.5 million parts, from tiny 5mm nuts to 20-meter fuselage panels. This system makes sure every component reaches the assembly line at exactly the right moment, helping Airbus maintain a production rhythm every 8 to 10 days. In the final stages, the A350 begins to transform into something unique for each airline. The vertical stabilizer is painted before installation because of its size, and once it is attached, the aircraft starts to show the identity of its future operator. Then come the interiors. In places like Hamburg, over 6 to 8 weeks, the cabin is customized according to the airline's needs. Some airlines choose luxury leather seats and premium layouts. Others choose high-density configurations with up to 440 seats. Some aircraft are designed with flat beds, bars, or even showers, depending on the operator's brand and strategy. The A350 cabin offers more overhead baggage space, LED lighting that can imitate natural daylight to reduce jet lag, adjustable windows, and entertainment systems with thousands of hours of content. Some airlines prioritize functional zones, such as space for hundreds of food carts or medical equipment, making sure each A350 combines efficiency with the identity of the airline that will fly it. Once the aircraft is fully assembled, the testing phase begins. During test flights that can last between 12 and 25 hours, pilots and engineers evaluate the aircraft through rapid climbs, controlled descents, and simulated emergencies, including turbulence and cabin system failures. On the ground, more than 4,000 checks are performed. These include pressure tests that replicate thousands of flight cycles, real-time satellite connection tests, and system checks across the entire aircraft. Adjustable water tanks are used to simulate the weight of passengers and cargo, allowing engineers to test balance and performance under different conditions. Only after passing every inspection, every test, and every safety requirement does the A350 receive its certificate of airworthiness. And only then is it ready to leave the factory and begin its life in the sky. What impressed you the most about the construction of an aircraft like this? Let me know in the comments. If you enjoyed the video, click the like button, and don't forget to subscribe to the channel. And in the videos appearing on the screen now, you'll find more episodes that might catch your attention. Go ahead and watch one of them. See you next time.